Hello community, rStar Mathematics Explained. And here we go, beautiful new paper I showed you in my last video and you sent me, hey, please explain this, we want to know this, so beautiful. So let's have a look here at Microsoft Research, rStar-Math. Small LLMs can master math reasoning with self-evolved deep thinking. My goodness, is this fantastic. But you know what we see immediately? There are dependencies that are not mentioned in the abstract, and there's some interesting wording. Let's have a look, explore this in detail. Now, we go here with the introduction of this paper. Thank you, Microsoft, and they absolutely correctly state, having here LLMs generate complete solution in a single inference run, which they also call System 1 thinking, often yields fast but error-prone results. This is from my last video here, typical LLM, trained, pre-trained, supervised fine-tuning. You have your reinforcement learning, your vector store, then you have all your private data in the database. And this is what's called a System 1 thinking when you have an answer generated within a second. But then we also learned, just in the next sentence, in response, test time compute suggests a paradigm shift towards a System 2 style thinking, which emulates human reasoning through a slower and deeper thought process. So here we have the test time compute from my last video. You see this is now here, if you want, here the System 2 style thinking. But as we'll see, this is incorrect, but never mind. So we have here then, this is taking 2 to 5, 6 minutes, maybe up to an hour. We just give the system time to think because we are not time critical, but we want that the system maybe comes up with a new molecular compound with particular pharmaceutical properties. So, how are the dependencies? You notice if you're a subscriber, I showed you with O3 Mini from OpenAI. They had to optimize their reasoning methodology already at the supervised fine-tuning and at the reinforcement learning with the synthetic feedback to optimize already here the System 1 thinking, quotation mark, to get a better System 2 thinking result. So we have strong dependencies because, surprise, surprise, if you optimize here 1 and 2, you get a better result than you just optimized 2. Great. You might say, okay, this was just OpenAI. In this video, I showed you here the new inference here, supervised fine-tuning, and the reinforcement learning by Google. We went how Google set this up, but you see in general, we don't go with a normal supervised fine-tuning or a classical reinforcement learning DPO, but we have inference optimized trainings. And if you want also here, I showed you that in this video, inference policy defines new reinforcement learning in test time compute. This here we have an inference that is now aware of a reinforcement learning. So we have some massive optimization. So if you ask, is there something new happening in level 2? Oh yeah, we have more or less retrained level 1 that we get a good result in the level 2 thinking. So we have massive training optimizations for your LLM. And then we come here to the third sentence here by the introduction from Microsoft, and I absolutely agree with them here, and they say here, in this paradigm, an LLM serves as a policy model to generate multiple math reasoning steps, correct, which are then evaluated by another LLM, and this LLM acts now as a reward model. And this is something, this is what we already do for years. We have here an LLM with a policy model. They generate here reasoning step, not just focused on mathematics like in this paper, but general reasoning step. And the evaluation of the reasoning step, which step is the best one, is happening with a reward model. We know this from OpenAI since 3-4 years. Now let's see this here in my visualization, and you might say, hey, wait a minute, this is absolutely compatible to your last video. Now, what a coincidence, no? Look at this. LLM as a policy model generates a multiple reasoning step. In my last video, we had this. Here at the test time compute, we had a chain of sort step, and then I told you if we go here in a tree of sort structure, then our policy model, this is an LLM. In the last video, it was the LLM itself. In this video, it is also the LLM itself that acts now as a policy model, generates multiple reasoning steps. 1, 2, 3, or if you go from this step, 1, 2, 3, 4. So this is the policy model. Now in this new paper, we will fine-tune the policy models continuously on each step. But this is just what's going to happen. So you see, we generate multiple reasoning steps, 1, 2, 3, 4. So we have a multitude of options where the perfect reasoning could happen, and you can then just follow along here in a tree structure, or I was working here already in a forest structure. And then here, we learn here from the paper by Microsoft, evaluated by another LLM acting now as the reward model. And you say, yeah, this is exactly what we had last video, no? Which of these 4 different reasoning steps has the best chance to come to the correct solution is evaluated. In my last video, it was the LLM itself that evaluated this when it found then some stop criteria defined by something else. But now in this paper, Microsoft tells us we have a classical reward model, although it is not classical at all. And there's now the beauty in this rStar mathematics model. But you see, in general, in the introduction, it tells us, we just follow here the classical path, how we do this. So we have here, if you go back, a policy model, and then in the next step, we have here a reward model that goes here and evaluates this, and the best path wins, as easy as this. Well, there's a lot of additional input to this. So in general, I just want to show you, implementing this is just what we know. This is a known procedure, even if we go not then simply with a tree search, but with a Monte Carlo Tree Search. We just have that we have a determined search algorithm or an arbitrary search function. So this is all known to us. There is nothing really specific new to this. So you might say, but now we applied now to mathematics, because here we have math and we have math reasoning. So it is now focused on mathematics. This is it. Yes, you are right. So let's start. Well known that off-the-shelf high-quality math reasoning data is really scarce. I don't know that not everybody loves mathematics. And synthesizing high-quality math data, there are some challenges, yes. And for the policy model, it is really challenging to distinguish here the reasoning step from the correct ones. Complicated here the elimination of low-quality data. And there are a lot of other reasons why we do not have the data for this. The training data are missing for a perfect high reasoning mathematical model. And then we have the term self-evolution. And when I see the term self-evolution, I get interested and I say, okay, so is self-evolution addressing here the creation of what? And the answer is of synthetic data. And we have a look, and then here, just look here at the latest here. This is from VentureBeat. And they say, this news here is also coupled here to the open sourcing of Microsoft's new 4 model, no? So while 4 releases has expanded access to high-performance small models, this rStar-Math procedure now, this methodology, showcases here a specialized approach using small AI system to achieve state-of-the-art results in mathematical reasoning. So you see, Microsoft is selling here this Phi model and the rStar-Math model here, according to VentureBeat here. Isn't this a coincidence that the marketing machine joined out this at the same time? Now, unfortunately, I've shown you here already a day ago in my community post. If we go here to Hugging Face and we compare here only on the open language model leaderboard, so if we have Microsoft 5.4 only on rank 508 of the open source LLM, maybe we need some additional augmentation. Why this is so perfect, and what a coincidence that here in the marketing now we have rStar Mathematics that is now pushed. And this is, you know what? You can use a small AI system to achieve state of the art of the big ones. Now what a coincidence, no? And now we have here rStar-Math leverages here smaller language models with the Monte Carlo Tree Search to establish here a self-evolutionary process. So we have a phoenix born out of the ashes of a small LLM, and suddenly it is as powerful, or more powerful than an O1. But wait, it is what? It's iteratively generating higher quality training data. So this self-evolutionary process is focusing on generating higher quality training data. Okay, so to answer this, the self-evolution addresses here the creation of synthetic training data. Okay, But maybe this is the first step. Maybe there's something waiting for us, no? And now we have 3 innovations by Microsoft. Let's have a look at this. So at each step, there's more language model, unbelievable, serving here as a policy model, samples now the candidate nodes here, each generating here a 1-step chain of thought and the corresponding Python code. And you might say, wow, this is amazing. Or if you're a subscriber to my channel, you know that already 2 months ago I showed you here exactly if you have any problem, not just mathematics, if you have a tool with Python, Prolog, Lisp, Scala, C++, function calling, if you transfer this to any coding, you can solve your problems here in mathematics in Python code. So math to code is maybe not such an innovation, but yeah, we are Microsoft friendly today, so hey, great that you innovated this. Okay. And then here we go, and they say, and here this is exactly from Microsoft, the screenshot here, a novel code-augmented chain of data synthesis method. And you might say, this sounds amazing. Here the marketing department is overtime. No. And you just remember in my last video yesterday, I always showed you this, no? Because remember, we looked here at this here, and we just said, hey, the LLM as a policy model generates multiple reasoning steps here, 1, 2, 3, 4, from a 1 chain of thought step here. And then we said, and then evaluated each step by another LLM acting as a reward model. We just had this, that now this is evaluated, and the best one or the top 2 candidates are now the successful ones that will here form the training data set. You might say, sounds like I know this, no? Yeah, but you know, here I generated the tree myself or the LLM. But now with this new Microsoft, we have the Monte Carlo Tree Search. And you say, okay, I get it. Yeah, absolutely beautiful. So you remember, policy model acts here as a node generator within the Monte Carlo Tree Search algorithm. So at every step, the policy model proposes the reasoning step that are then evaluated, since we are doing here mathematics, using simple here a Python environment, and we can immediately find a solution. Now this simple way of Monte Carlo Tree Search provides here a quality value, we know this since 2 years, from Q star for each step, indicating its contribution to the correct final answer. And the authors say, hey, we refine the Q values by iteratively evaluating each step over multiple rollouts. And I will tell you how many rollouts there are in detail in a minute. So if a step leads to the correct answer, the terminal node leads to the correct answer, then its Q value, its quality value is increases. Otherwise, it is decreased. So, simple example, reinforcing the correct problem-solving patterns. This is all there is to it. But then, and this is now, I think, really crucial, you know, it's not using anymore the classical reward model. Why? We cannot calculate the absolute reward to these mathematical problems. So what we do, we take something that we know from BERT. Yeah? We have now preference pairs. And a pair consists now of a good one and a bad one. So instead of giving you here the absolute reward expressed here as a single reward value of, I don't know, 4.7, whatever this is, we have now multiple pairs where the system just learns, hey, this is a good solution and this is a bad solution. So we call this now process preference model instead of a reward of the classical reward model. And the preferences, we have good preferences and bad preferences. And this tuple is perfectly for an LLM to learn the pairwise ranking loss function that we already encountered when we learned BERT. So you see, what a coincidence, it always comes back more or less to the same algorithms, to the same idea. Now, I have to give credit to Microsoft because I think the training process itself has some inherent beauty. This is really nicely done, independent if they use known procedures, but you have to design the training process, and I think they have really achieved here some nice insight. Let's have a look at round 1. Now, if we're at the initialization phase, so we have an initial policy model, this is our small language model, by the way. So at this stage, we're just beginning. There's no dedicated math reasoning policy model. Where should it come from? So in round 1, Microsoft decided to use here a strong publicly available open source DeepSeek Coda version 2 instruct model. This is a 236 billion free trainable parameter code LLM. You might think, this is nice, but this is not really a small model. No, but this is a detail. Come on. And then Microsoft goes on and says, hey, the number of MCTS rollouts per mathematical problem, we set now to 8 for speed of computation, as the training data at this point need to be produced at very large scales. And I will show you the training data set in a minute. It is almost 1 million data. So here we use now a DeepSeek Coda 236 billion for starting the process. So it is not that the little 7b small language model starts from scratch. But this is a dependencies that is not really mentioned. But I think for us, for you and for me, it is important to know how the model starts. So we start here with a real heavyweight that produces now results. Then we come to the code-augmented chain of thought approach. So at every step, now our new policy model that is already available, our DeepSeek 233B model, generates now two things. At first, for the chain of thought, the reasoning pathway for every single step. So a natural language description of the multi-step chain of thought solution, plus, since we're talking about mathematics, the actual code for every natural language description of the mathematical problem to execute for the action. And then it is easy, because we have math, we have immediately the Python code, and then we just execute this Python code, and if the Python code executes successfully, then the step is added because it is the correct step. So here, the generated chain of thoughts serve now as the training example that consists here of the generated natural language description of each and every step, the generated Python code generated by the 236B model in Python, and the execution output that we have here, a validation, is it successful or not. So you see, the whole process starts with a monster coding LLM that provides here for a particular set of mathematical problems, I think more than 700,000, natural language solution, step description, complete code, and evaluates everything. Great. Now, in the initialization phase, if we want to talk about rewards, we don't have any reward model, because I will show you later that in Microsoft publication, the reward model is the policy model with a new specific head. So we have nothing yet there. And since there's no PPM available, now Microsoft decided here to go for the classical solution, a terminal guided annotation, which simply assigns here a specific quality value, the Q value. This is the initial reward signal in Monte Carlo Tree Search of, you will not guess it, +1 for successful and -1 for failed trajectory at the final leaf node in the Monte Carlo Tree Search. And if we found the good solution, then we have a standard equation to back propagate here through the complete tree, and wherever it is successful, we simply increase the quality value of particular nodes. So those edges and those nodes become more prominent, and the system knows now, if I follow this path with these edges and in these nodes in the tree search algorithm, then I have a higher probability here that I can do exploitation compared to exploration, where we will have here an upper boundary Monte Carlo Tree Search formula, where we will also look here at nodes that are not as prominent yet, but maybe they give us here the perfect solution. So this Monte Carlo Tree Search is here a beautiful balance between exploitation and exploration in the search space. Beautiful. Now, you know, if you are a subscriber of this channel, that here in August 2024, I already showed you here from Harvard University, beautiful author here, and Microsoft, that they already had here exactly the same idea, and they also called it already rStar. So this is here the predecessor half a year ago. And they were already talking here, making smaller LLMs stronger problem solver. And they had more or less the same idea, but look here, they go here, decoupled reasoning into self-play and the Monte Carlo Tree Search with a rich set of human-like reasoning actions. So we were more or less bound here by a lot of human quality evaluations. And now in the new rStar mathematics, because we can transform mathematics to Python code, and Python code we can execute and see if it's the correct solution, yes or not. We have now syntactic data and syntactic reasoning actions and syntactic nodes and edges in our Monte Carlo Tree Search algorithm. And therefore, trajectories we can verify and validate. So you see, August 2024, we have rStar, and January 2025, we have rStar Mathematics, now with this not anymore on human annotated, so here complete syntactic data. Now this was round 1 on the dataset generation. And now comes the most important part in round 1, now that we have the syntactic data, as generated by our 236 billion monster of a code LLM, we have now the training data for a little tiny 7 billion small language model. So if they say Microsoft claims here they train a 7B model from scratch, I would say, okay, I mean, if you forget that your first step was a 236 billion pre-trainable model that gives you here all the solution, and from this multiple solution, you only take the top 2 trajectories. So the best 2 multiple step solution in the mathematical reasoning that have the highest Q values. Okay, if you forget that this is your very first step and you take this data and this are the trajectory, that on this you fine-tune now your new small base 7B model. Okay, if you forgot the step, then you do it from scratch. Yes. I don't think that the marketing department had here anything to say here in the publication of this journal. Okay, but since we are here a science channel, let's come to the results. And I think the results are really interesting. So here we see it now. This is here table 3, accuracy of the resulting policy small language model in each round. So let's start. You have here all the different benchmarks you can think of, beautiful. But this is not as important because here now, deep in the paper, they show you, okay, so we start with the 236 billion code LLM. And their model itself has a particular performance on all these benchmarks. This is the first line that you have. And then we choose here, well, Microsoft decided to go with the Qwen 2.5 Math 7B. Interestingly, they chose here the DeepSeek and then the Qwen as the best models to showcase their new methodology. Interesting, Microsoft. Yeah, and then comes now the part. So we just had here the round 1. This is what I showed you, no? With the fine-tuning now, we ended now with the fine-tuning of the 7B, given the training data generated here by our DeepSeek code version 2 instruct. So we reach now here, let's say here in the first, an accuracy of 69.6. Great. So you see, from the original Big Brother performance, we made a significant jump now, because the base Qwen 7B, if it's not pre-trained on the result here of DeepSeek, has 58. So we jump here almost here from 58 to 6 to almost 70%. This is nice. So if you say we built from scratch Microsoft, I would say this is a free interpretation of a semantic detail. And then we have now multiple rounds, round 2, round 3, round 4. And now, if you want, this is where the self-evolving is happening. So just to be sure, very simple explanation. We fine-tune now with each step the small language model and the policy model and the PPM model on the best data that we get at each round. So with the Monte Carlo Tree Search, we have a rollout now of 16. So this means we have for each particular mathematical problem 16 possible solutions. And maybe there's only a slightly derivation in the reasoning path to come to the correct solution. But given that we have 16, permutations, minimum permutation here, if you only select the best 2 of those 16 permutation, the hope is, if you continue this multiple times, you only take the best 2 out of 16 or out of 32, that you can increase it. And this is what's happening. Look, 69, 73, 75, and 78. And now we reach the point where we are higher than the original base model that we started from. We are better than our 236b. 75.3, 78.4. However, it could be that this is not happening, as you see here in this benchmark data. The original model that Microsoft started with has 57.5. And after doing the same thing, they're not even close to the base performance. So here this methodology fails. But you can also have here something like this one. Look, here the base model has 94.9, real good. But even the base model of the 7B has already 91.6, which is really good. But then if we apply now this new R-star mathematics to this model, you see on this test here, on this particular mathematical test, you see we do not even get close to the base 7B model before we started with all of this. And we are far away from the bootstrap model, our DeepSeek coder version 2 instruct. So here we fail completely. So just to show you how sensitive these success data are that you see published, given your particular benchmark data, the benchmark methodology that you choose. Yeah, dataset. So they start with 747,000 math problems with final answer ground truth labels given. So here we go now. So each round, R1, R2, R3, R4, uses Monte Carlo Tree Search to generate step-by-step verified reasoning trajectories, because we do this in Python code and we know exactly if Python is working or not, which are then used to train the new policy, small language model, and the PPM. And you know now, that tell you, behind the policy model and here the preference model is our classical small language model. They just have different heads. And now the new models are then applied in the next round to generate high-quality training data. So with this fine-tune, this continuous fine-tuning every step, we really now change here the tensor weight. We really kind of do a learning that is happening deep inside our layers of the transformer, and it is not in-context learning. It has nothing to do with RAG. This is now really happening in a fine-tuning process. And I think this is a beauty of this model, because we have now a continuous iterative fine-tuning of the small language model of our 7B model. But this takes time, just to be clear now. This, if you want to have this model here on your particular domain expertise, on your domain knowledge, this takes quite some time. And now you understand why Microsoft went with a 7B model. So the PPM is also initialized from the fine-tuned policy model, which is next token prediction head is now replaced, as I told you, by a scalar value head in the transformer layer, consisting here of a linear layer with a tangent hyperbolicus function to constrain the output to the range of -1 to +1. And therefore we have now beautiful, if you want, our reward model, our preference model in place. And if you ask why no 4 data, why they go here with a Qwen and a DeepSeek, I cannot give you an answer, because it would have been beautiful, no? To show the performance of 5.4 here and how the performance of 5.4 increases. This would have been a win-win situation for Microsoft, but I guess there was a reason why they did choose not to go this way. Now let's look at this self-evolution thing that still fascinates me here through this multiple rounds, and we have 4 rounds, as I've told you. We went together now with round 1, round 2, round 3, round 4. nothing particular happening. We just repeat here every step. Now that we have in place our PPM, now that we have a perfect here Q value annotation happening, you just have to let the system run, and we apply here the training method with the Monte Carlo Tree Search and the PPM, as already explained in my visualization here in the beginning and the middle of my video. So you do this 4 times. If you want, maybe you do it more. It is an interesting methodology. It has pros and cons. Let's have a look at the pros first. We have a data quality focus, which is really good because the system tries here with the Monte Carlo Tree Search and the backpropagation here, and here the modification here of the quality values here, to always find the best reasoning trajectory, and therefore generating very high quality training data. Yeah, we can go here in this mathematical augmentation with synthetic data. We have scalability, emergent abilities, well, yeah, performance and generalizability, great. We rely heavily on the Python code and the generation of Python code given a natural language formulation. The better your code LLM is, the better will be your Python code and the better will be the quality of your system. As I told you, we have iterative continuous fine-tuning so that your computation cost, even Microsoft states, computation cost can be computationally intensive. You have a strong dependency on the initial policy model strength. This initial policy model is our 236 billion free trainable parameter model, and whatever we know where DeepSeek shines is great. But if DeepSeek has some problems or some biases, those biases will be immediately transferred to all the other models. Bias, limitation. Yeah, the model shows problems in geometry, of course, and visual understanding. How you encode, now how you code in Python here the visual content or 3D geometry in Python. So you see, yes, this is working great for mathematical problems, but for geometric or visual understanding, currently there are still research to be done. What I was thinking quite a lot of are the dependencies that this rStar-Math has on the DeepSeek 230B model. And can we get rid of this? Can we make it really beautiful? That our small language model are really outperforming even the bigger ones. We have at the beginning the results of the 233B Monte Carlo Tree Search path with a Python code and an execution verification for all the intermediate steps in the reasoning path for each single mathematical query that we have. So this 236B model generates here each and every intermediate natural language reasoning step. And these intermediate steps are evaluated by the sparse terminal reward function we were talking about, but only selected portion of that data that contain the correct code and the code verified intermediate steps and the correct answer are used for the training. So let's say we have 4 correct solutions, only the top 2 are selected from all valid solutions. This is what I said before. If you have 16 permutation and you only take the best top 2 permutation, so you are really only focusing on the top. And now the whole idea is, if we continue this multiple times, finally we reach here with the 7B model a performance that is maybe 1 percentage point or maybe 2 percentage point above the 236B model. So there you have it, rStar mathematics explained in detail with a little bit of dependencies and a little bit of a twist here and there, but otherwise a really interesting paper to further optimize your test time computation, to increase here the mathematical performance even of small language model. And if you are interested in this topic of small language model, maybe subscribe and you will be surprised by my next video.